Yeah. Hi, everyone. I'm John Duncan. I'm actually on the customer success team here at Voxel 51. I work directly with our enterprise clients to help them integrate their machine learning workflows within 51. Um, some of whom use audio. So I'll be talking today a bit how you can use Voxel 51 to integrate your machine learning workflows in your audio machine learning workflows and giving some specific examples from what we've learned from some of our clients. So without further ado, I'll give a quick overview of what 51 is in regards to audio, and then I'll dig into the bulk of this presentation, which is 4 audio ML tasks. First is representing audio. Second is audio curation and similarity search. Third is audio captioning. And then the fourth task that I'll look at is audio moment retrieval from long form audio. And then I'll kind of close with some summary and conclusions and next steps for anybody who's interested. Now, some ground rules. All of the materials that you'll see today are available on GitHub. So that's here in this meetup repo. So that contains the data loader scripts and some of the other things that helped produce the results that you'll see. So that's all in this meetup demo. And then there's a more generic 51 audio toolkit that I've been working on that can includes some operators in 51, a custom embedding search panel that I'll show you, and a spectrogram renderer. So no need to take notes or anything like that. Just know it's kind of all there. I did want to be very upfront about this. This is actually more of a data and tooling platform discussion and not necessarily research focused. So my goal here today is really to show you what's possible within 51 and not necessarily to achieve a specific research goal or anything like that. Also, as a word of advice, it is very hands-on. So I'll be transitioning between this slide deck and live demo of 51 Enterprise. So first, I'm going to assume most of you have probably heard of 51, but for those of you who haven't, it's an open source toolkit to visualize, curate, and evaluate machine learning data sets. Many of the common workflows that you'll see in 51 include things like data curation, annotation, applying model inference to data sets, and then, of course, evaluating the results of those model inference runs. As Jimmy said, it was originally designed for images and video, so a lot of our heritage is directly related to computer vision. However, we've expanded pretty substantially recently into multimodality and physical AI with native support for robotics data types and so on. Audio is not natively supported yet. However, many features that I'll show you today are available for audio using custom extensions of Core 51. So not natively supported, but definitely possible to execute many machine learning workflows within 51 for audio. Quick word about semantics that I'll be using. A sample in the context of audio in 51 is a single audio clip. Data fields are additional metadata that's stored on a sample. So in this context, things like labels and captions and evaluation scores can all be stored directly on the sample fields themselves. A data set is a set of samples that's organized around one task. So I've got data sets today for audio classification, captioning, and moment retrieval. A view is a smaller focused subset of data. So if you take a specific data set and cull it down a little bit for specific conditions, that's called a view. And then finally, you'll hear me talk about the software development kit, operators, and plugins. And these are all ways that we can use to extend Core 51 functionality to implement these audio features. So with all that said, I'll get right into the first task, which is how we represent audio in 51. As I said, 51 does not have a native audio media type. If you try and load a group of WAV or MP3 files into 51, it'll hit you with the media type is unknown. So there are actually two methods that I'll show you today for how you can represent audio with 51, each of which has their advantages and disadvantages. The first is using a custom sample renderer class. So this was introduced in 51 Enterprise 2.18, so it is the paid version of the software. And what it does is it draws a spectrogram and gives an audio player directly in the grid, does the Fourier transform directly within the browser, and it works for all your major audio types. So this is what it looks like. Each one of these is a short wave audio clip, and you can browse and see the spectrograms there and kind of get a quick overview of some of the features. And if you click into one of these individual samples, you get a player. So you can see here it's something that you can just play and inspect here. As they talked about in the last talk, I wasn't able to pipe the audio in from the browser directly into Zoom here, but you'll have to take my word for it that that's actually a dog. So this is kind of how you can quickly and intuitively browse your data sets within FiftyOne using that custom sample renderer. The next method is you can convert your audio files to MP4 files using FFmpeg. And what this does is it renders the full clip as a spectrogram video with an audio track. And as I mentioned, we have a lot of tools available to process computer vision, so images and videos. And if you do this, it allows you to use those tools. So here's the same data set using that MP4 renderer. Looks very familiar. If you hover over it, you get a preview of the video. And then when you click into it, you get a few options for how you can play the video. So first is, you can just play it. You can specify the playback rate. You get some information on where the clip is going. You can loop it. You can show the frame number if you want. So all the same information, but just a slightly different look and feel for how the samples are. So here they are kind of side by side. There's the renderer, and here's the MP4 conversion. One thing I wanted to show here before I move on to the next topic is that this is the ESC50 data set. So it's 50 unique classes, 2,000 clips total, and 40 samples per category. This label category is provided with the data set, so I can put that alongside here and just kind of look and see what the actual spectrogram and audio file correspond to in terms of label. So this FiftyOne classification is kind of the first and simplest type of label that you'll find in FiftyOne, and it's kind of a prerequisite for some of the further supervised learning tasks that you might need to perform. So that's kind of the basics of how you can import audio files into FiftyOne. So building off of that, what I'll show you next is how you can curate your samples and do audio similarity search using embeddings and a custom panel that I developed. So back on that ESC50 dataset, I want to talk about embeddings. So we use embeddings a lot for our computer vision tasks, but you can use them for audio as well. Embeddings are basically a very rich feature vector that encode a lot of the information from the audio file, and they provide you a means of identifying clusters and outliers. You can compute them directly within the app by delegating them to a runner if you use the enterprise version. You can also do it via an SDK script. For this one, I've used clap and MS clap embeddings. And the reason why is that these two embeddings specifically bridge the gap between raw audio and language. So it allows us to do natural text search of some of these raw audio files. So going back here, I'll show you first the embeddings panel. Have the option to select either the clap embeddings or MS clap embeddings that I've computed. So let's look at the MS clap ones. And as I said, this begins to show you some clusters. And if we color them by the category label, you can see that right away, each one of these individual clusters correlates to a specific label. So it gives us some pretty good separation of the classes themselves. And another core FiftyOne functionality is you can just lasso these. And the grid view here is updated to reflect that. So this particular cluster is thunderstorms and knocking on wood and clapping. So really like percussive sounds. I do want to show you my custom panel though, which also kind of builds on this. So I'll keep my embeddings view up down here just to give you a visual indicator of what's happening. And then up here on the top right corner is my custom embedding search panel. What this allows you to do is either select a sample, upload an audio file, or just give a text prompt. And then you can search your data set for samples that are similar to that one. I've already computed the embeddings for dog barking. So that was just an example that I gave just because my dog's sitting next to me and like that was what was in my mind at the time. So I've computed the embeddings for this text prompt, and I can go and compare that text prompt to every other sample in my data set. And the result here is a histogram that I can interact with where the x-axis is the distance from that text description that I gave, which is a dog barking. And then the histogram values show me what's actually in the data set. So if I start to expand this search boundary outward, I see some samples start to pop up on my embeddings field, and I see dog samples that start to show up. So that's a good indicator that my text prompt is good and it's starting to retrieve relevant samples here. And then it looks like I got one pig sample there too, so I can start to expand outward a bit more. I'm getting some animal sounds here, so I'll pick dog and pig and hen and cat and sheep. I'll keep expanding that outward. And I can use this method to not only explore the embedding space, but kind of mine for positives and negatives. So if I'm looking to train an audio model that recognizes dogs, it probably might be worthwhile to find things that are similar in the feature space, but like really hard cases to test against. And this is kind of a core FiftyOne thing that we like to do. So I'm going to select these and crickets, and I'm going to call that sounds like dog. And I can copy that tag and create a custom view. So now I have this view where it's all these 76 samples that sound like a dog, but it's not. And likewise, I can unselect these. And I'm going to select the other ones here. So these are also, again, negative samples. They're not animals, but they are kind of close to it in the embedding space. So I'm going to call that sounds like dog, but isn't. And basically, this is a method that you can use to mine for positive or negative samples in the embedding space. And it came directly from one of our enterprise customers. And of course, just to kind of close the loop here, if you expand this out even more, you get even more samples that are increasingly further away from things that are even remotely close to animals. And then we see that here. So that's kind of the second task I wanted to show you, which is how you can search the audio embedding space using FiftyOne. Third one is audio captioning. So as I mentioned, we have the ability to represent lots of data types as fields on individual samples. So what I've done here is I've loaded the Clotho dataset via a custom data loader script. And for reference, each one of these clips is 15 to 30 seconds of varying complexity. It's all synthetic data as well. Out of the box, it includes a captions field, which is 5 human descriptions of what is contained in that audio clip. And ground truth is the primary reference caption that's selected from that. So it's kind of the main caption that's used for supervised learning further on. I ran a custom script that applied the Kinet model and then generated predictions. So this is what the model thinks is actually happening in that WAV file, converted to a caption. And then the final thing I did was ran a custom evaluation script that uses the AAC metrics. So these are commonly used in like DCASE challenges for semantic and similarity and accuracy for captioning classification tasks. So all the references are here, and I'll go ahead and show you what that looks like within FiftyOne. So clicking into the sample, I'll show you yet another custom plugin. This one is called the Caption Viewer, and this allows us to see a text field alongside it. So I can look at the ground truth, and then I can compare that against what the prediction is. So the ground truth in this case is a person is rummaging through the pans while looking for something, and then I can add another instance of this caption viewer and show what the model thinks is happening here. So now I've got this nice little custom view where I can just skip through my samples. I can listen to them. I can see what the ground truth is, and I can see what the prediction is. So this is kind of like a nice visualization function for how you can do that. But the main thing I really wanted to show you here was how we can explore these captions. So as I mentioned, I ran an evaluation on all of these to compare how accurate the predictions are compared to ground truth. And anytime you have a predictions field and a ground truth field, you can do something like this to compare the accuracy. So I'll show my embeddings here, just like I did before, and I'm going to use this fence accuracy metric, which is compares the semantic accuracy of both the prediction and the ground truth. And I have this interactive histogram at the bottom right. And what this is this is literally the distribution of semantic accuracy for this data set as evaluated. So towards the right end, these are my really, really accurate samples. And towards the left end, these are the inaccurate predictions. So I'll click on the right side and let's see what some good predictions look like. I can also just overlay the accuracy score directly. So I'll look at my most accurate prediction. And it's word for word the exact same caption. Crickets are chirping and a dog is barking in the background. The only difference here is some capitalization and punctuation. So all in all, a very almost perfectly accurate example. As we start to skip through here, I'm just looking for trends here in kind of what's represented in the data. Birds are chirping, cars drive by. A swarm of bees buzz around. And again, the caption is not quite exactly the same, but it's semantically close enough that it gets a high score on this metric. So again, birds, vehicles. I mentioned this just because, just like in computer vision data sets, computer audio data sets have a lot of common type classes too. So we've got kind of nature sounds, animals, humans, vehicles, and these all tend to perform well because they're represented in the data. So those are the good examples. I wanted to show some not so good examples now. So I'm going to click at the very bottom end of this accuracy distribution, and let's also look at those. And you'll notice too, the embeddings panel updates. So we can see kind of where those samples are distributed amongst the data set. And one key pattern is that good examples and bad examples are kind of distributed all across the data set. So that's something to be aware of. So looking at this one, this is the really low accuracy example. The ground truth is that a hairdresser is blow drying and handling the hair of a customer. So a very, very specific instance. The caption is a bird is chirping in the background while a car is driving by. So again, a really strong edge case here where it's a hairdresser and like a barber salon or something like that. But the samples that we actually have in our data are things like nature and vehicles. So that's kind of what this caption predicts. I can also listen to it too. And honestly, it's as I mentioned, it's a synthetic data set. It's very rough. I would say it does sound more like insects. So it's synthetic and it's also kind of a bad sample, but also possibly getting these bad results because the data is just not really covering this edge case of like a hairdresser. Moving along here too, ground truth is a match is struck repeatedly but never catches fire. It predicts that somebody's opening and closing a drawer. Again, very specific kind of edge cases. They're probably not captured very well in the training data. So I'm not surprised to see that these are some of the examples that do not perform very well. Likewise, remote control car, very specific edge case. Person with an electric saw. These are more common things that you might find in the data. But main thing I wanted to show you here was that you can use this to inspect and find not only what's good, but kind of gain some insight and intuition about where your data are and the results that you're getting based on your model. So that's task 3. I'm going to move into our final task now, which is audio moment retrieval. So the task is actually motivated by DCASE 2026 task 6, which is given a long clip plus a text description of something happening in that clip. Find the matching indices of when the moment starts and ends. So you're given the clip, you're given the description of what's happening, and it's up to you to figure out it's up to you to figure out when that happens. So for this one, I actually use the spectrogram video viewer, and in FiftyOne that allows us to use some of the native timeline and audio and temporal detections classes that we use for videos. So some useful primitives that come out of converting this to video. So that's why I did it in video. My approach was very, very simple and pretty rough here, kind of like a minimum viable product. But basically what I did was I computed embeddings per frame, and then I just slid this window along the entire clip to generate a similarity curve over the entire data clip, basically. And then I used that to find a window closest to the query at each timestamp. There's like 4 parameters that are tunable here, so it's a very, very coarse approach that I didn't optimize or anything like that. However, this is just kind of the intent here is really just to show you what's possible within FiftyOne and how you can represent this task and some of the data types. The metrics here actually came directly from the panel, and I'll show you how I got those, but a couple things to note. It's not a large data set. It's really just the validation split, and the full methodology is covered in the GitHub repo. But moving along here, you'll see a couple things. So if you see, the purple is ground truth, and the pink is predictions using the clap embeddings, and gray is predictions using the MS clap embeddings. So ground truth plus 2 prediction methods. And those bracketed numbers on the left and right are just the start and ending indices of when it thinks that event happened. If I click in a bit further, I'm going to look at this annotate tab. And as I mentioned, that gives us this interactive timeline where I can see ground truth in purple, and then the magenta and gray here are the 2 model predictions for the different embeddings methods that I have. And I can just scan through my entire data set like this and really look for anything that jumps out one way or the other. And I can also use the evaluation methods to compute the overlap here. But just to kind of show you, like I can click here and then just zoom directly to the moment of interest and play it back. And you can also like loop over this specific instance and just shrink the window and just play this one clip of interest. So these are all tools that are primarily for video annotation, but you can use them for audio clips as well. So I wanted to highlight that here. Speaking of evaluation, we have a model evaluation panel, which many of you might have used for computer vision tasks, but you can use it for supervised audio classification as well. And that's what I've done here for both my clap embeddings method and my MS clap based model. So if I click in, I get the high level metrics of how this method performed. Kind of your standard accuracy, precision recall, F1, and your mean average precision. I also get a nice confusion matrix where the on diagonal elements here are true positives and true negatives, and my off diagonal elements are my false positives and false negatives. So all of these are clickable, by the way. So I'm going to click on this panel to show my false positives. And then the grid view is filtered here to show all those false positives just kind of intuitively. And then I can click in and then just inspect kind of what's happening with these. So just wanted to highlight here, these numbers came directly out of the panel itself. There was no additional evaluation script that I needed to run or anything like that. All right, so here's all my false positives. I'll click in on one and have a look. And yeah, so here's the ground truth, and it's pretty obvious in the spectrogram where the ground truth actually is. And then here's my model prediction. So right off the bat, you can kind of tell they're not overlapping very well. They're shorter, and there's just the boundaries aren't correctly identified. So again, like I said, it was a very, very kind of basic and coarse technique that I implemented here just to show these predictions. And I can view the results right here in FiftyOne and the evaluation metrics. So quite a bit that we can do with all these. So this is actually the final thing I wanted to show. So moving on here, key takeaways. All the core FiftyOne data types and workflows that you're used to can be extended into the audio domain to kind of help you with some of these audio machine learning tasks. I talked about representation, so using a custom renderer, but also the spectrogram video renderer, embedding search using clap and MS clap, using natural language descriptions to search the embedding space and retrieve positive and negative samples. Captioning, I talked about how we can inspect both the high and low quality predictions and then surface some of the data quality issues and kind of just build some insight about what's in our data set. And then the last one I just showed you was the moment retrieval, and specifically how you can use timeline tools for video and the evaluation panel for video to apply them to audio moments as well. But if you take nothing else away from today, just know that there are a range of audio machine learning tasks that are possible within FiftyOne. The sky's the limit, as Jimmy said. So I love talking about this stuff. So please, if you're interested in audition, computer audition, robot audition, don't hesitate to reach out. I'm the only John at Voxel 51 at the moment, so that's my email address. I'm also on GitHub. I'll share the repos here. But a lot of exciting things that are happening in the field now. So if you're doing like sound source localization, multi-channel audio separation, any of that stuff, acoustic scene recognition, I really, really like working on this. So would love to work with you all and kind of build off what we discuss here.